In exercise 616, they're asking us to not just recognize patterns for curved arrows, but to draw the curved arrows in order to make the changes that are shown in each reaction. Now the first step is to identify all of your nucleophiles and electrophiles. That'll help to see how things are connecting. So first, for nucleophiles, we have no full negative charges. We do have a partial negative charge on the oxygen here. We have lone pairs on the oxygen, and we don't have any pi bonds. I'm looking in the reactants. So those are our only nucleophiles. For electrophiles, we have a full positive charge, and we have partial positive charges on each of these hydrogens. Well, already we can see what's going to happen. This nucleophile, this oxygen, only has one thing to attack on the other molecule, the electrophile. And you can see that in the product, that is indeed what happened. You took the water and you formed a new bond from the oxygen to the carbon. So to draw the curved arrows, always start by drawing the tail of the curved arrow at electrons on the nucleophile. Remember, curved arrows show the movement of electrons. They do not show the movement of atoms. So you want to make sure that whatever electrons are moving are always drawn in. Put the tail of the curved arrow at the nucleophile and have the head of the curved arrow point at the positive charge on the electrophile. And that's the full curved arrow. That's all the curved arrows that you need to explain that transformation. So notice that there would be classified as a nucleophilic attack. All right, let's try it with B. We're going to first we're looking at our reagents. Remember the stuff on top of the arrow. That's a new way of writing reagents in organic chemistry. So we're just looking at those, just those. And what we want to do is identify the nucleophiles and the electrophiles. Okay, well, do we have any full negative charges? No. Partial negative charges? Yeah, we have a partial negative charge on that oxygen. The other oxygen actually is pulling electrons to itself, but because it has more bonds than it would normally have, it has a positive formal charge. So that's for partial negative charge. How about lone pairs? We have two lone pairs on the water oxygen. We have one lone pair on the oxygen in the molecule. And pi bonds? No pi bonds. So that's it for nucleophiles. How about for electrophiles? Well, we do have a full positive charge on this oxygen, although the oxygen already has an octet. We have partial positive charges on the hydrogens because they're losing their electrons to that oxygen. And we have partial positive charges on each of these hydrogens. Okay, so now hopefully it's a little clearer what the ways things that may react. So now we can look at the products that they're giving us just to be 100% certain, because you might imagine a couple different scenarios here. To be 100% certain, look at the water. It has 2 hydrogens, and the product, it has 3. Notice the oxygen on the carbon chain in the reactants has 2 hydrogens, and the product has 1. So clearly what's happening here is a proton transfer. So you take the nucleophile, the water, it's going to take a hydrogen, always draw the tail of the curved arrow starting at the electrons in the nucleophile. The curved arrows show the movement of electrons, not of atoms. And you point it at the head of the curved arrow at the positive charge of the electrophile. Now that hydrogen is only going to be able to form one bond, so if it's going to form a new bond to the oxygen, then it has to break the bond that it already has. Those electrons go on to the most electronegative place nearby, which is that oxygen. And so those are the curved arrows you would need to explain that transformation. Let's try C. Now in C, we only have one molecule on the left. If we were to look for nucleophiles and electrophiles, you could say, okay, well, we have a lone pair. We don't have a full negative charge. We don't have a partial negative charge. We do have a lone pair on the oxygen. We don't have any pi bonds. For electrophiles, we have the full positive charge, and we have partial positive charges on these hydrogens, and also on this carbon. I might have forgotten to put that here. You would have had that partial positive charge on that carbon that's bonded to the oxygen. So we have that, but the thing is this has nothing to react with. This is all by itself. So let's look at the products to get a little direction. We notice that in the products we have two different molecules. We have a carbon chain that's all by itself and a water that's all by itself. So what must have happened is this water must have left the carbon chain. It must have taken those electrons in the bond. Those would go onto the more electronegative atom in the bond. That's the oxygen. And that would give it a second lone pair here. And it would leave behind a carbon with a positive charge. So that's a loss of a leaving group. Those are all the curved arrows you'd need to draw to explain that transformation. So that is 616. Let's continue that with 617. And these four reactions, there are four here that we're going to want to draw the curved arrows for. These four reactions we're going to delve into in detail in the next couple chapters. The next chapter will be these first two, and the chapter after that we'll be talking about these next two. Very common reaction type. So outside of the context of those chapters, you could see already in this chapter, you could figure out what's happening here by drawing curved arrows. So let's think about it one at a time. First, let's identify the nucleophiles that we have in the reactants. The chlorine has a full negative charge, and it has 4 lone pairs. The bromine is also pretty electronegative. It has a few lone pairs of its own. It's pretty electronegative. It's all the way on the right on the periodic table, so it's slightly negative. It pulls electrons away from the carbon then, which becomes slightly positive. Let me actually write that here. And so those are all of your nucleophiles, all of your electrophiles. Now, even if you didn't look at the products, you could see what's going to happen here. This nucleophile is going to be attracted to that electrophile. So notice, you always draw the tail of the curved arrows at the electrons on the nucleophile. Curved arrows show the movement of electrons, and the head of the curved arrow pointing at the positive charge of the electrophile. So tail at the electrons on the nucleophile, head at the positive charge of the electrophile. That carbon already has 4 bonds. Carbon, carbon, bromine, and 1 to hydrogen. It's not being drawn in. It's implied. It already has 4 bonds. If it's going to form this new bond to the chlorine that the curved arrow is trying to communicate, then it has to break one of the bonds. And you can see that the bond that breaks is to the bromine. And that should make sense. You take the electrons, well, first let's talk about why it makes sense. It should make sense because bromine is really big. Chlorine is the size of a methyl group. Bromine is even larger. As you go down in a column, the atoms get larger. So it can take that negative charge and it can spread it out, its enormous size. And as that charge spreads out, it becomes more stable. So that bromine is going to break off. The electrons in the bond go onto the bromine, the more electronegative atom. Notice that the tail of this curved arrow is not starting at an atom, it is starting at the electrons in the bond. It's crucial. The biggest mistake, the most frequent mistake in drawing curved arrows is to show the movement of atoms when actually curved arrows only ever show the movement of electrons. So you always want the tail to start at electrons. You actually have 2 curved arrow patterns happening here. You have nucleophilic attack, and then you have loss of a leaving group. Both of those are happening at the same time in this reaction. Okay, let's look at the second one. We only have 1 molecule to start with. When we look at what it becomes 2 things. The bromine that was attached goes off on its own. That's loss of a leaving group. The electrons in the bond go onto the more electronegative atom, which is the bromine. So that's the first step. Now, it's true, this bromine is a nucleophile, and so with its negative charge, it will attack the electrophile, the positive charge again, which is why this is an equilibrium reaction. It'll pop right back on and give us our molecule back. But that wouldn't give us any net change. Another thing that could happen is the chlorine, which also has 8 lone pairs and a full negative charge, that can attack our electrophile, which is this full positive charge here. Always draw the tail of the curved arrow starting at electrons in the nucleophile, and the head of the curved arrow pointing at the positive charge in the electrophile. Let me draw that a little more clearly. It should be attacking that atom. So there we have nucleophilic attack. And so you end up with this here. Notice those are the same two steps as we had above. It's just in B they're happening one at a time. In A we had nucleophilic attack and loss of a leaving group happening at the same time. In B we have loss of a leaving group and nucleophilic attack happening one after another, one at a time. Notice the result of both reactions is very similar. You start with a bromine on the carbon chain, you end with a chlorine. Start with a bromine on the carbon chain, you end with a chlorine. You substitute the bromine with a chlorine. Okay, let's look at this next one, C. So here we have our full negative charge on this oxygen. The R here, an R in organic chemistry is like an X in math. X in math means any number. R in organic chemistry means any carbon chain. So notice the power that comes, notice the profound implication of writing that. The implication is that the carbon chain doesn't matter. If you have a negative oxygen, that will always have the same behavior. It will always be attracted to positive charge, no matter what the carbon chain is. So here, that if you were to analyze this writing in the nucleophiles and the electrophiles, you would say, okay, the chlorine is slightly negative, it's stealing electrons from that carbon, which is slightly positive. And as we'll discuss in this future chapter, the nucleophile truly does attack that carbon there. The nucleophile attacks the electrophile. But another thing happens too, and that's the thing that you have to show in this reaction, because that's what will give rise to these products. They show a double bond forming. The way a double bond forms here is if this nucleophile doesn't attack the slightly positive carbon, but instead does a proton transfer. It attacks the hydrogen. The electrons in the bond to the hydrogen go toward the positive charge, which they're attracted to, and they kick the chlorine off of the molecule. So you have two things happening here. You have a proton transfer, and then that, like a set of dominoes knocking down, leads to the loss of a leaving group. So those are the curved arrows you would show for this reaction. And the result is you have a chlorine on the molecule in the beginning and you don't in the end. Instead you have a double bond. You took the electrons on the hydrogen, you made them a double bond. So proton transfer and loss of a leaving group in C. And in D, similar thing is happening. Notice in this first step we only have one molecule and then the chlorine comes off of it. So that's going to be loss of a leaving group. So the electrons that are holding the chlorine on, those will go onto the chlorine, which is more electronegative than the carbon. That's how you get this minus Cl minus. Notice, leaving, that's what the minus sign is there. It's leaving our view. It's still in the container, bumping around with stuff, millions of other molecules, but we're not interested in the reactions it has. Our focus is on the carbon molecule. So we have loss of a leaving group in that first step. And then in the second step, you have your nucleophile here, the oxygen, slightly negative with lone pairs. And if your hunch is that that attacks the electrophile, you're right, that does happen. Some of the time that does happen. But another thing happens too, and they want you to illustrate the other thing here. You know because of the products they give you. Here they give you a double bond. They don't show the water molecule attaching to the ring. Instead, they show the water molecule gaining a hydrogen. So what happens is the oxygen attacks the hydrogen. Always draw the tail of the curved arrow at the electrons in the nucleophile, the head of the curved arrow at the electrophile. That hydrogen is losing electrons. Those electrons go toward the positive charge to help to stabilize it. And so here, that would create the double bond, and it would give rise, you'd have this step of a proton transfer. So notice in C and D, you have the same two curved arrow patterns. In C, you had proton transfer and loss of a leaving group, but they happened at the same time. In D, you have loss of a leaving group and proton transfer, but they happen one at a time. Otherwise, those are the curved arrow patterns for these 4 reactions that we'll have a lot more time to talk about in future chapters. So remember, when you draw curved arrows to show how a reaction happens, make sure the tail of the curved arrow is always starting at electrons in the nucleophile, and it's always pointing to the positive charge